Okay, so today I want to talk about principal components analysis and more generally matrix factorization methods and dimension reduction methods. The first thing I want to talk about is a view of principal components analysis that goes through the singular value decomposition. So that's my preferred way of looking at principal components analysis. So I should say there are other ways that go through the eigen decomposition of a covariance matrix, and they are kind of equivalent if you're careful. But I like the singular value decomposition version. So that's what I'm going to start by talking about here, what the connection is between the singular value decomposition and the eigen decomposition, which we've already looked at, and how by doing singular value decomposition of a data matrix, you can often get useful summaries of the data, maybe some useful plots, and that kind of thing. So the notation is that X is going to be an n by p matrix. So think about n samples and p measurements on those samples, maybe. An example we'll look at later is that we've got the zip code data. So n will be the number of images we're looking at, and p will be the number of pixels in each image. And we're going to just ignore the fact that an image is a square. We're just going to vectorize it. So just take the pixels and just, in this case, there'll be 256 pixels. So just think about it for now as a vector of length 256. We will actually visualize the image as a matrix later, which is actually how the image is, of course, because the pixels are arranged as a square in a 2D array. But for now, just imagine each row of our data matrix is a digit and each column is a pixel. And if you remember, there's some kind of normalized grayscale level for the images. Okay. So a singular value decomposition, every data matrix, any n by p data matrix has a singular value decomposition, which is a decomposition of this form. It's unique. And the decomposition is of the form that the U's here have orthonormal columns, and the V also has orthonormal columns. So V transpose, the V dash here, the dash means transpose. So the V dash has orthonormal rows, and D is an R by R diagonal matrix that kind of think of that as kind of analogous to the eigenvalues. It will turn out to be analogous to the eigenvalues, or at least the square root of the eigenvalues. Okay, so any data matrix X, any matrix n by p matrix has a singular value decomposition, and you can find it relatively efficiently. The computation is kind of something like np squared, where n is the bigger dimension, or pn squared, something like that. Roughly n cubed if it's a square matrix. And in fact, there are very interesting fast ways of finding approximate singular value decompositions, or what's sometimes known as truncated singular value decompositions, using modern randomization-based methods that are even faster, that can work on very, very big data matrices. But you don't need to worry about that for now. Let's just assume we can find that decomposition. So what properties it will have? Well, because of the orthogonality, you get the X transpose X, just multiplying it, you get V D U transpose U D V transpose, and because U transpose U is the identity matrix, that's equal to V D squared V transpose, and V is orthonormal. So you can see that this is actually the, and X transpose X is a symmetric positive definite matrix, or positive semi-definite matrix always. So you can see that actually, if you know the singular value decomposition, you also get the eigenvalue decomposition of X transpose X. Sorry, where V are the eigenvectors of X transpose X. And just doing the, pardon me, Pardon me. Yeah, so just doing the math the other way, you get that XX transpose, which is, of course, is now an n by n matrix, because X is n by P, is equal to U D squared U transpose. So both ways, you get the eigenvalue decomposition, the eigen decomposition of XX transpose or X transpose X. So that's the connection. If you look at the V's, it's like doing finding the eigenvectors of X transpose X. If you look at the U's, it's like finding the eigenvectors of XX transpose. And that's why that some people do PCA by doing an eigen decomposition, but I like to think about it in terms of the data matrix because it makes it easier to connect it with other methods, I think. So if you see PCA, if you've seen PCA done in terms of the eigenvectors of the covariance matrix, that's the connection with doing it this way. Okay. So there are some very interesting properties here. So actually, the first K terms of this matrix, so if, sorry, I should say the D's, if we arrange that the D's are increasing in size, sorry, decreasing in size. So D1's the biggest D, and D2's the next biggest, etc. Then this sum here is the best rank K approximation to X in Frobenius norm. So Frobenius norm means sum of squared errors. So this is a matrix here. It's a rank K matrix because it's, sorry, this. Apologies. This here, this sum is a rank K matrix because it's a sum of K rank 1 matrices. Each U's a vector, V's a vector, Uj is a vector, Vj transpose is a vector. So this is a rank 1 matrix. And D's a scalar, Dj is a scalar. So this is a sum of K rank 1 matrices. So it's a rank K matrix. It's the best rank K matrix that in terms of matching X in Frobenius norm. So you just take the sum of the squared differences between this matrix and X, the X matrix at each element, square them, sum those squared values. That's the Frobenius norm. That's here. Okay. So so if you take K equals 1, if you just take the first U and V and multiply it by the corresponding D, you get the best rank 1 approximation to X. And when you add in the second one, K, the first one plus the second one, you get the best rank 2 approximation to X. When you add in the third one, you get the best rank 3. So it's a very nice kind of hierarchical structure where you get the best rank K approximations nested. Okay. And so in a way, one way of thinking about this is that the first K columns of V are in some sense a really good basis for representing the rows of X. So I say the columns of V, that means the rows of V transpose, the rows of this matrix here. They're a good basis for the rows of X. And the U's are a good basis for the columns of X. What do I mean by good basis? I mean that the rows of X can be quite well approximated by some linear combination of the first K rows of V transpose, or the first K columns of V. Okay, so that maybe that's a little hard to get your head around. So let's have a look at an example here. This one, the SVD. Having trouble clicking. Okay, so this is the zip code training data we looked at earlier. I've just looked at the images that are either a 2 or a 3 here. So that's what this code does, is extract the images that are 2s and 3s. And I do an SVD on the data matrix. That's this one. The first column are the labels of whether it's a 2 or a 3. So we don't want that. We don't want that. That's not part of the data. That's the labels. So SVD is we're doing SVD on the pixels, which are the other 256 columns of the data matrix. So we just do the SVD, and here what we've done is plot the first singular vector, or the left singular vector, the The u's are called the left singular vectors and the v's are called the right singular vectors. So we're plotting the first left singular vector and against the second left singular vector here. And the color here is the label. So either 2 or 3, right? Because so 2 is red in R, so the 2's are colored red and the 3's are colored green. So this is what you get when you plot this. So what you can see is that this actually the first singular vector doesn't really separate out the 2's versus the 3's. We'll see why that is in a minute. The second singular vector, or sometimes would be called the second principal component. Actually, people often ignore this one, and this one would become the first principal component. But this eigenvector here separates out pretty well the 2's from the 3. So it's a direction in the space. You can think of it as a direction in space that separates out the 2's from the 3's. So just remember, each point here is an image, right? We're looking at we're plotting their values along the 2 first eigenvectors. So let's think about it this way. We're using 2. So we're going to try and, the way to think about it is we're going to try and represent each image as a linear combination of 2 quotes eigen images. Right? So that's the way to think of this. Let's get rid of that. Okay, so let's see what we're doing. We've got a data matrix. So each row is an image 1, is an image. So that's image 1, image 2, image 3. Okay, and these are pixels here. Okay, column. And so they're arranged as because of the data matrix, the pixels are just arranged as a vector here. So we've got data here, and the idea is we're trying to write. You can write it as let's say, so the first one will be U11 D11 V1 dot, let's say, plus V1 dot means that vector of values, and maybe I should be V transpose 1 dot. Let's not worry about it. That's here. I mean, by V I mean the rows of V transpose. Okay. So this is the first row of V transpose. And then we're going to have a U12, D12. Let's just put these together because they're just a number of V2 dot. So the idea is we're trying to find these, think about it this way, we're trying to find these eigenvectors or these basis vectors, V, each of which is a image, basically, because it's a set of pixels, quotes an eigen image, right? So we think of each V as an image, and we're trying to represent image 1 as a linear combination of these 2 eigen images. So, just think about it as we're allowed to V1 plus lambda 1 plus lambda 2 V2. And we've got to do the same thing for every image. We're going to write every image as a linear combination of 2 quotes eigen images. And you have to find what are the best eigen images to use so that you can do that as accurately as possible, right? And that's what SVD is solving. Simultaneously, it's solving for the lambdas, which are the U's and the D's, right? But think of it that way. We're looking at these lambdas or these U's in that plot, which is, so how loaded, sometimes these are called loadings, how loaded is each image on those 2 eigen images. Okay, so let's go back to this SVD thing. So that's what these are. These are those U's, those are the loadings, the 2 values. Each image is loaded somewhat on the first eigen image, that's the x-axis, and somewhat on the second eigen image. And what you can see is that most of the green dots have a positive loading on that second eigen image, and most of the red dots have a negative loading on that second eigen image. Whereas they all have kind of an almost equal loading on the first eigen image. And that's, if we look at the, if we look at the eigen images, you can see, okay, they're a little bit difficult to get your head around, but you can kind of see an element of maybe 3s in there, some kind of level of 3, and maybe also a level of a 2. You know, there's an overlap of, if you imagine putting a 2 and a 3 on top of one another, maybe there's something around here. And so I haven't played with the colors as much as I could to maybe make this as clean as possible. But what you actually expect these eigen images to look like is roughly you expect the first one to be kind of an average of all the images. So that's an average of all the 2s and the 3s. So it looks a bit messy as an average of those. Because if you really had to choose one image so that every image can be represented as a linear combination of one image, you're kind of best just choosing the average and just using a linear combination of essentially a constant, same, you know, which is why these, roughly speaking, I mean, it's not exact, but roughly speaking, these, you know, they're very similarly loaded on this first image. And you can think of that image as roughly the mean of all the images. And if you had to, I mean, you obviously wouldn't get the interesting differences in there, but if you had to summarize a bunch of images by some multiple of a single image, you kind of can see that maybe taking the mean image and then just representing each as a multiple of 1 times that mean might be about as good as you can get. Yeah. And then, so then the intuition is that the second image is going to have to, if you're given a second image, you can represent this collection of images, which are 2s and 3s. If you can capture the difference, the difference in mean, let's say, between the average 2 and the average 3, then you could represent your 2s as the mean plus the difference between 2 and a 3. Maybe I need to write this down. So if if you can get V equals, a 2 plus a 3, an average of, and V2 equals the difference, let's say, between 2 minus a 3, then you can write every image as, if it's a 2, you write it as half V, and I'm not being careful about normalization here, so, but just to, so a 2 here would be the average of those 2, and a 3 would be the difference between the 2, right? V1 half V1 minus V2. So you could write, if you could capture that, you can kind of get an average 2 and an average 3 out of these 2 eigen images. So that is what's going on here, is that the first image, although it might be a bit hard to see, is kind of an average of all the 2s and 3s, and this is like a difference between the average 2 and the average 3. So you can kind of see in some kind of shape to it, but it's a little hard to interpret, right? And that's why the 3s, I guess, the positive loading on the difference versus the negative loading on the difference. So that's coming from that second, that they're roughly speaking, waving my hands a little bit, everything's loaded on the first one positively, and then some of them, sorry, I didn't mean to erase that. Some of them positively loaded on the second one, and some are negatively loaded. Or if we switch V2 to V3 minus 2, you'd get the other way around, which is equally good. So there's some ambiguity about what the signs should be. They're equivalent. The representations are equivalent. You can just switch all the signs of all the V's and switch all the signs of all the U's, and you get the same singular value decomposition. So the singular value decomposition is unique up to that kind of sign issue. Okay, so that was an example 1. So what I'm trying to get you to think about is that this is kind of representing each data point. Think of each image as a data point here. Each data point is being represented as in terms of a new basis, in this case, just a basis of size 2, V1 and V2. And so you get 2 numbers for each image. So you really get a very kind of a data compression, if you like. You get compression of the data. And that's what this plot is doing, is kind of taking that original data matrix, compressing it down to 2 dimensions, and then plotting the results in 2 dimensions, right? Which is 2 dimensions, a very convenient way place to plot things. So so this is a very common technique, is to, when you want to visualize a data set, when you first got your data set, is to do a singular value decomposition on it and just plot the first two eigenvectors against one another, either in this case image space, or you could do it in pixel space, but that wouldn't make much sense in this case. You know, the pixels, for our case, the pixels, you're visualizing the images in this case. Okay, so here's another example of that. Let's look at another example, which is this map of Europe here. So that's this image. Oh, sorry. Okay. Better not. Okay. Can't. I was trying to blow it up. I can't make it any bigger. Maybe. Okay, well, let me tell you about this image, and you can see a better version of it in the original article here. This image is just the first two eigenvectors, the first two principal components here, computed from a data matrix that's genetic data from Europeans. So you think of each row of the matrix is a person, and each column is a position in the genome. And what we've measured is if they have 0, 1, or 2 copies of a particular allele at each position in the genome. So it looks pretty much like those elephant data we looked at earlier, but these are real data. And because they're real, everyone has 2 copies of their genome, one they got from their mother and one they got from their father. So you have, at any given location, you have 0, 1, or 2 copies of a particular genetic type called an allele. So the data matrix is a series of 0s, 1s, and 2s. So when you do SVD on this data matrix and remove the first one that's just the overall mean, and look at the next two, the first, usually called the first 2 PCs. So in I guess this would be 2 and 3. The first one, I like to include the first one because I feel like it keeps, it keeps this kind of consistent interpretation of what's going on as an approximation to the data matrix. But some people, remove the mean first and then do the singular value decomposition on X with say the means of the columns removed. But I don't like to do that as much because you have questions of whether to remove the column means or the row means or things like that. So I prefer to do the SVD as I mentioned. But okay, so but do the SVD and then I kind of ignore the mean, which is the first eigenvector. And look at what's left. And what you can see here is that when you plot the individuals and then you color them according to where they came from in Europe, or actually these individuals, each of them had 4 grandparents that came from the same country in Europe. They were chosen to have that property. So you plot where their 4 grandparents came from. You color them according to where their 4 grandparents came from. You plot them here according to the PCs, which are done without access to those labels. So the colors are the quotes labels, like the digits were labeled. These are like the labels of where each individual came from, or their grandparents came from, where their genes came from is essentially the way to think about it. And so those are the colors, and you're just plotting them according to where they fall in this kind of genotype space, or these PCs. And so what you see here is if you go and check the locations, the colors against a map of Europe, what you see is that the individuals are kind of falling geographically in this space. It matches the geography of the original space. Okay, so it's kind of a cool result that these individuals here are from Spain and Portugal, which is here on the map, and these individuals up here are from Britain and Ireland, which is up here on the map, and these individuals down here, I'm not sure where that's, actually I'm not sure where that is. Italy here, this is Italy, etc. So I think this is Greece. I'm not 100% sure. Yeah, not sure. So, but anyway, largely speaking, this map, this principal component plot matches pretty closely to the geographic map. So actually, the reason for that is essentially just to do with the eigenvectors of circulant matrices again. It's going back to that same thing. So sorry. So it's an analogous result to the circulant matrix result, but it's in 2 dimensions instead of 1. So if you remember what we did last time on circulant matrices is if you have data that's on a circle, that's a 1D structure. A circle is kind of a 1D structure. It could be a line, but circle gives you the exact result. But if you have data along a line where individuals that are closer together on the line are more similar to one another, that is, the distance decays with the similarity decays with distance, the covariance decays with distance, then the eigenvectors of their covariance matrix are the eigenvectors of the discrete Fourier transform. And if you remember what the eigenvectors look like, they look, depending on exact, they look something like kind of this kind of thing. So, so actually, if you plot the first eigenvector is roughly quotes distance along the line, and the second eigenvector here is distance from the center of the line. This is like distance along the line, and this one's distance from the center, or distance from the edges. So, so actually, if you plot the first eigenvector against the second eigenvector for data that follow a 2D structure, you get this kind of, sorry, a 1D structure. You get this kind of picture. So actually, I've got another example of that from some real data. Right? This is here is a plot. This is a real data set taken from my genetic collaborators, and each point on this plot is taken at a given time. So each sample is taken at some time from 0 to 15 days. Actually, the data are on cells that are being treated so that they become like heart cells. So they start off as skin cells, I believe, and then they get treated and reprogrammed to become as heart cells. So at time 0, they look more like, well, actually they're called induced pluripotent stem cells at time 0. And then over time, they're treated to make them look more like heart cells. So, so what you have is that at day 0, the samples that are the cells that are taken at time 0, they're all kind of similar to one another, and they're more similar to the ones at time 1 than they are to the ones at time 2. So you get this kind of time series where each day is the cells are more similar to one another and to cells in nearby days than they are to days that are far away, because they're changing over time. And so when you do a PCA and plot PC1 against PC2, you see this kind of horseshoe shape, exactly because it's kind of mimicking these Fourier. It's like a horseshoe. So it's sometimes referred to as a horseshoe effect. In fact, it's pretty useful to know about, because otherwise you might look at this and you might wonder why is there a horseshoe here? PC1 versus PC2, and sometimes it might go this way instead, or some variation on this. But the idea is you can just think about, it's really trying to represent a linear kind of trend, or a linear linear trend in the data in 2 dimensions using this horseshoe shape. So that's in 1 dimension. In 2 dimensions, it turns out there's an analogous result. So to the circulant matrices. So the matrices become more complicated, okay? But it turns out that now the eigenvectors are related to the discrete, what's called the discrete cosine transform. And bottom line is that maybe if I plot it in 2 dimensions, it's a bit hard to, essentially, if you've got data in 2 dimensions, so each point is a data point. Sorry, think of these as the people. So each point is not a data point. Each point is a person that came from somewhere in Europe. But we've got genetic data on each person. We might have 100,000 genetic markers on each person. So for each person in space, got a lot of data. And the individuals that are nearby are more similar to one another than individuals that are far away genetically, at least on average. So it's the same structure as that time series where the cells that were taken from day 1 were more similar to the cells from day 2 than they were to the cells from day 15. And there was a kind of a temporal continuum. Here there's a kind of a spatial component, right? So people are more similar to other people nearby one another than far away on average. So what happens is that the eigenvectors reflect that, and in fact essentially the first eigenvector will be, kind of measure distance in one direction, and the second eigenvector measures distance in a perpendicular direction. And exactly what the orientation of those will be depends on things like, your sampling scheme and how, if you had data spread out like this, you might see this kind of direction. But in any case, pretty robust result that you'll see the first 2 eigenvectors after you've removed the mean to reflect position in 2-dimensional space. So that's what's going on here. That's what's going on here. We're plotting the first 2 dimensions of works. What we're seeing is that the kind of data, that the similarity between pairs of individuals is reflected in this 2-dimensional, think of it as a projection of the data. Okay, so this is, if you really want to get into the details, this paper here describes all the details. Actually, these ideas are related to the way that images are compressed using JPEG compression. So you could also have a look at that. I'm going to stop there because the video's already gotten quite long. So basic summary is that people use PCA or SVD to form a dimension reduction or a low rank approximation to the data. And so oftentimes in particular, they plot the first few eigenvectors against one another to get a low dimensional kind of image like this kind of thing. And that one of the reasons to do this is just to check that the data that you've collected match things you might know about it. So here we would hope, right, that the 2s and the 3s would be more similar to the 2s would be more similar to other 2s, and the 3s might be more similar to other 3s, and so we can have a quick plot like this in PCA space to check that.